Assalamualaikum and hi everyone. My name is Ahmad Daniel bin Abdullah.
And my name is Muhammad Adam bin Abdul Mubin.
And today we're going to present on the SPSI mini project. So for the objective of this project is to simulate the power management of a parallel hybrid electric vehicle using a maximum SOC control algorithm. So for the first part, I will explain on how this code works. So without further ado, let's get started. So we have used the I/O stream to provide the functionality for standard input and output of operation, such as the C-in or C-out. For the F stream, it is to use to reading from or writing to file using streams. And then we need to use also vector to provide the vector container from the C++ standard template library. And then we also need to use SSStream to get the easy conversion between strings and other data types. And then finally, we also use CMath for the mathematical functions such as power or square root. So we opt to use the using namespace std to simplify the code by omitting the need to use the std prefix. So as you can see here, this is the main function of our code. Basically, for the first line of couts, it will display the program description and what will be the output for this program. Next, we also declare constant where it will be used throughout this code and the value doesn't change. And then we also use the constant for speed threshold where only the battery will be used, and also the acceleration threshold where both the battery and fuel are used. So basically, the last two is for the power controller. And then we also need to declare variable that will be used in this code. Basically, for the whole section, it is to prompt and get the input from the user. And then in this part, open the input file, either it's UDDS drive cycle or the HFET drive cycle. It's basically to find the file from the same folder as our code, such as for this is SPSI UDDS project. So basically, if we want to use the highway life cycle, we just need to change the UDDS to HFET. Next, we also included a checking error to check whether that our file is opened successfully or not. And then we need to initialize vector such as all this line. And then from that, we can read and pass dev cycle data from the input file, where the variable will be stored in each line, read from the file using the string line. And then we use while loop to get as long as the file has a line, it will keep on going and checking to get the needed time or velocity, as you can see here. So if the attempt to extract time and velocity is successful, we use the predefined function of vector, which is pushback. Basically, it will push the element to the last element or the last index of the vector. If the extraction is failed, it will print an error message and exit with the error code. Next, we create and open a CSV output file using offstream output file. In this case, in this first part, we use output UDDS basically to show you the output for the Urban Daily Dev cycle. However, if you want to use the HFET, you just need to change the name from UDDS to HFET. Basically, there will be two separate Excel file where you can open to maybe plot or analyze the data. And as always, as the input file, we also included a checking error to check whether that the file is opened successfully or not. Next, we use the CSV header row basically to create a header for each of the row separated by the comma, which is the comma is the delimiter. And then we initialize the previous velocity and time. And then we use for loop as long as the I value is smaller than the size of velocity of the times vector, this loop will keep on going. So here, as you can see, we have included all the needed calculation. And for this part, torque calculation, if the velocity is 0, we set the torque to 0 to avoid division by 0. Otherwise, the calculate torque using the power at the waist and velocity is used using this formula. And then for gear selection, actually we find that the most similar car to our group requirement is Lexus RCF. So it's quite hard because this is a sport car, and then the top speed is only 150 kilometer. So we just like use ratio to get all this value. And then for this value for gear 1, gear 2, until gear 8, it's basically from the manufacturer list. You can find it on Google. And then we use a ternary operator to determine the appropriate gear ratio based on the current gear. Basically, this is a shorter version of if-else statement. And then we use to calculate the engine speed, the engine torque. And then we calculate the efficiency of ICE, which is the internal combustion engine, using the efficiency map given in the Excel file. The first if statement is to check whether that the torque is non-negative, meaning to say that they generate power. So in this if statement, we calculate a threshold value based on the polynomial equation given in the Excel file. So after that, we will check for not a number or infinity for the efficiency of ICE and set to 0 if it's true. And then we multiply it by 100 for percentage representation. And that's moving on to the next part, which is the state of charge calculation. As you can see here, this is the first power controller, which is whether that the vehicle is operating below the battery only speed threshold. And inside that, we got a nested if to check whether that the vehicle is stationary or moving. So this is the code if it's stationary, and this one is for if it's moving. And then we got for the second power controller, which is whether that the acceleration is more than dual power threshold, meaning to say that it will both uses the fuel and the battery pack. And then there is the third power controller to say that if the car is in acceleration, however the SOC is 0, it will use the fuel and doesn't use the battery. So as you can see for all of these three, we have loaded the ensure that the SOC is within the value range is between 0 or 100. As you can see from here, is with added that if the value is negative, the program will set it back to 0. If it's more than 100, it will come back to, or it will set back to 100. And then just calculate the distance using this formula. And then we will route next, we will write the data to CSV file using this. And the delimiter is comma, where it will separate each one of this value in each different row. And then we just need to update the previous value. And then the loop will go up again, and it will keep on going until the end of this time vector size. And then we can close the read file and output file. And then we included a cout to inform the user to let the user know that we have written the data to Excel file. So before we proceed to the live demonstration of our code, I think it's a good idea to explain on the challenges and difficulty that our team has faced for this mini project. So with that, I will pass the floor to Adam.
Okay. So now we'll proceed with the difficulty challenges faced by us in coding this program. First, finding the correct formula to be used in the project. For example, there are many formulas that we can use to find power at will. Therefore, we took more time than expected to get the formula, the correct formula. In the end, we chose the one that will give the closest value to the example given in SFI. Second, we can also use more power controller or conditional statements to make the code more comprehensive and cover all the possible driving conditions. For instance, we could have include a power controller that ensure the car will use fuel instead of battery when SOC is low in charge during acceleration, or when the traction power is more than power that is optimal for the engine. The car will be in hybrid traction mode. However, we don't include all the possible power controllers as we found that we get illogical value from the output. Thus, we only include a few power controllers to cover the basic of the distribution of power between fuel and battery pack. Last but not least, we can also use a function to calculate SOC or energy use to make the code shorter, and we can always call the function when needed without having to write the same thing again. However, when we did that, the output values are far off from the example given, so we opted to not include the function in this program. Now we will proceed with the running of the program made by us. Right, so as we can see here, this is the code which was presented earlier by Ahmad Daniel. So first we will run through the UDDS, and as you can see, this is our like default code which we will read and write on the UDDS file. So now we will run the program, and as you can see, the program will ask the input from the user. And for our group, we have chosen this input, the black highlighted as our data. So we will fill in all this input into our program. Right. So as you can see, the data returned to SFR. So we can close this window and then open the file. So as you can see, here is the output of our UDDS file. We can open the file. So here is our data from the code which was made by us, right? So after we get this code, this data, we can create graph as shown in example. So here is our graph for time versus velocity and power at will. This for graph time versus current and state of charge. This is time versus wheel torque in Newton meter, and finally this is the graph for time versus distance. Right. So to run for HFET file, we need to like changes in our code, which all the UDDS need to be changed to HFET. Right. So change that. Right. So now all things changed. I think we can run the code. Right. So we'll proceed with the same procedure. Right. So now data returned to SF file. So as same as with the previous, we now have output for HFET. Right. So we can open the SF file. Right. So this is the data for our HFET, and pretty much the same with the for UDDS. We can make our graph from there. So this is our graph for time versus velocity and power at will. This is graph for time versus current and state of charge. This graph for time versus wheel torque. And finally, this is our graph for time versus distance. So I think that's all for our mini project. Thank you.